In January of 1986, 7 people climbed into a spacecraft, and the whole world was watching because one of them was a schoolteacher going to space for the first time ever. And 73 seconds later, all 7 of them were dead. And for months afterward, the most powerful space agency on the planet stood in front of Congress and basically said nobody could have seen this coming. It was a tragedy nobody could have predicted. And that would have been the official story forever except for one man who refused to accept it. A physicist who did not work for NASA, who had no political career to protect, who just wanted the truth. And he found it not with a supercomputer, not with classified files, but with a clamp. A glass of ice water and a piece of rubber smaller than your fingernail stick around, because by the end of this video you are going to understand exactly how Richard Feynman took down an entire agency using nothing but grade school physics and common sense. They told the world it was unpredictable. He proved in about 30 seconds that it was painfully predictable, and almost nobody wanted to hear it. Let's back up, because to understand why this moment mattered, you have to understand who Feynman actually was. He was not some outsider who got lucky. He had already won the Nobel Prize in physics. He had worked on the Manhattan Project as one of the youngest scientists in the room. He was famous for cracking safes for fun, for playing bongo drums between lectures, for explaining the most complicated ideas in the universe using diagrams simple enough that a teenager could follow them. People did not call him eccentric as an insult. They called him that because he refused to accept an explanation just because someone important said it was true if the math did not check out. He did not care whose name was attached to it. So when the Challenger exploded and a presidential commission was formed to investigate what happened, Feynman got a phone call asking him to join. And honestly, he almost said no. He was already sick at the time, though he did not know just how sick yet, but something about the case bothered him. The official explanations felt rehearsed. The language felt like it was designed to protect an agency rather than explain an event. And that is the kind of thing that made Feynman's brain itch. He could not let it go. Here is the open loop I want you to sit with for the next few minutes. The actual physical reason the shuttle exploded is almost embarrassingly simple once you see it. But the reason NASA missed it or ignored it is the part that will genuinely disturb you, because it was not really about science at all. It was about pressure and schedules and people convincing themselves that risk was smaller than it actually was. And we are going to get to the exact moment Feynman exposed that. But first, you need to understand what actually failed. The space shuttle was not one solid rocket. It was built in segments. Think of it like a giant metal tube made of several rings stacked on top of each other. And where each ring met the next one, there had to be a seal, something flexible, enough to expand and contract without ever letting hot gas escape. That seal was a rubber ring called an O-ring, and there were 2 of them at each joint, as a backup in case one failed under normal conditions. Those rubber rings were supposed to be springy, almost like a fresh rubber band. They would compress when the rocket ignited, then snap back into shape, sealing the gap perfectly. The entire safety of the launch depended on that little ring doing its job in a fraction of a second. Now here's where the story gets uncomfortable, because engineers working on the shuttle program had noticed something troubling in earlier flights on colder days. Those O-rings did not seal as well. Sometimes hot gas would actually blow past them slightly, leaving burn marks that should never have been there. This was not some secret sitting in a locked drawer. This was known internally months before the disaster. There were memos. There were warnings the night before. Launch engineers on the ground even argued that it was too cold to fly. Safely, temperatures were forecast to drop into the 20s, which was far colder than any previous launch. And they said this out loud to the people making the decision. And still the launch happened. This is your first pattern. Interrupt. Because I want you to picture something familiar. Think about a rubber band you keep in a drawer. In summer, it stretches easily. It snaps back instantly. Now put that same rubber band in your freezer for 20 minutes. Take it out and try to stretch it. It barely moves. It feels stiff, almost brittle. That is not your imagination. That is real physics. Rubber becomes less flexible as it gets colder. It takes measurably longer to return to its original shape. And if you are using that rubber to seal a joint holding back thousands of degrees of burning rocket fuel, a half-second delay is not a small inconvenience. It is potentially catastrophic. That was the entire mechanism. Engineers were worried the O-rings would not snap back fast enough in the cold to seal properly during that critical first second of ignition, and that is exactly what happened on launch day. Burning gas escaped through a joint that did not seal in time. It burned through structural supports, and less than 80 seconds later the vehicle came apart in the sky. So if this was already suspected, why did NASA tell Congress the failure was essentially unforeseeable? This is the twist, because it was not really a lie, in the sense of someone inventing a false story. It was something more human, and honestly more frightening. It was an organization that had convinced itself through repetition that a known risk was an acceptable risk every time they launched in cold weather, and nothing catastrophic happened immediately. It reinforced the belief that maybe the danger was smaller than the engineers thought. Risk assessment inside NASA had quietly drifted from, "we know this is dangerous," to, "well, it worked before, so it is probably fine," and that quiet drift is exactly the kind of thing that gets erased once tragedy happens, because nobody wants to admit that normal operating procedure was the problem. Now we get to the tour. The moment this video promised you, the hearing room was packed with officials, reporters, cameras from every major network. Testimony had been going on for days, full of technical jargon and cautious phrasing. Engineers speaking carefully, lawyers speaking even more carefully, everyone choosing words that avoided direct blame. Feynman sat there mostly quiet, taking notes, running his own numbers on the side, because something about the testimony did not add up to him. The material properties being described did not match what he understood about how rubber actually behaves at low temperatures. So during a break in testimony, without asking permission from the committee chair, without any dramatic announcement, he reached into a glass of ice water sitting on the table in front of him. He pulled out a small clamp with a piece of the exact same O-ring material compressed inside it. He had prepared this quietly beforehand. He squeezed the clamp, released it, and everyone watched the rubber slowly unfold instead of snapping back instantly. It visibly hesitated. It took several seconds to attempt to return to shape, live on television in front of the very people who had just spent days explaining why cold temperature was not really a meaningful factor. He did not need a single slide. He did not need a single classified document. He needed a glass of water from the table in front of him and about 15 seconds of silence. That moment became the single most replayed clip from the entire investigation, because for the first time, non-engineers, politicians, reporters, ordinary people watching from home could see the problem with their own eyes. It was not abstract anymore. It was not buried inside 100 pages of engineering reports. It was rubber in ice water failing to do the one job it had. Here is your mid-video reset, because you might be thinking, okay, cold rubber, bad seal, that is the whole story. But the deeper lesson Feynman pushed for afterward is honestly the part that should stick with you the longest. He was not satisfied with just diagnosing one physical failure. He wanted to understand the decision-making culture that allowed engineers to raise alarms and still lose. He later wrote in his own section of the final report that management's estimates of the odds of failure were wildly more optimistic than the engineers actually building the hardware, while engineers on the ground were estimating real meaningful risk of catastrophic failure. People higher up the chain were treating the odds of disaster as something closer to negligible. That gap between the people closest to the danger and the people making the final call is the part of this story that still applies far beyond rockets. Think about how often this exact pattern shows up outside of NASA. The people doing the actual hands-on work know something is risky. They say so clearly, and the people approving the final decision are further away from the technical reality, more focused on deadlines, budgets, and momentum, and slowly convince themselves the risk is smaller than it truly is. That is not a NASA-specific flaw, that is a human organizational flaw, and Feynman basically forced the entire country to watch it happen in real time using nothing but a physics demonstration a child could understand. Now, here is the climax, because after Feynman's independent findings, there was actually resistance to including his blunt language in the official report. He wanted plain, direct wording about the disconnect between engineering estimates and management estimates. Some on the commission wanted it softened, smoothed over, made to sound less confrontational. Feynman essentially said either his full, unedited findings go in the report exactly as written, or his name would not be attached to it at all. In the end, his section was included largely as he wrote it, becoming Appendix F1 of the most famous individual contributions ever attached to a formal government investigation, and it remains one of the clearest public examples in history of a scientist refusing to let institutional pressure quietly reshape the truth. What happened after is honestly bittersweet. Feynman passed away not long after the investigation was finished. He never got to see just how influential his blunt, honest approach would become in engineering education risk assessment and safety culture discussions for decades afterward. The demonstration itself, the simple ice water test, is still taught in engineering classrooms today, specifically because it captures something calculators alone often cannot: the danger of trusting a system just because it worked yesterday. And that is really the whole point of this story. It is not just about a rocket or a rubber ring. It is about what happens when the people closest to a warning are ignored by the people furthest from the consequences. It is about how the most complicated failures often trace back to something almost embarrassingly simple once someone finally has the courage to demonstrate it in front of everyone, instead of burying it in a report nobody will read. If this kind of story hit different for you, the kind where real physics explains something far bigger than the equation itself, make sure you are subscribed, because this channel is full of stories exactly like this. Drop a comment and tell me what you would have asked Feynman if you were sitting in that hearing room. And if you learned something today, hit like. It genuinely helps this channel keep making videos like this. Thanks for watching, and I will see you in the next one.